Okay, hello again. So now we just want to look at running QTQt, and we're going to start with building data files. So just looking again at this file menu, you see at the bottom is a series of recently opened files. It's up to 10. And the options we have here, we can open an existing QTQt data file, we can build a new data file, we can review a data file to see what's in it, and we can add things to that data file if we want to. We can take a hefty data file and convert it to QTQt. But that only works for the hefty data files that are in text format. So I think the HFT data files are in binary format, and that won't work here. So only the text versions of the hefty data files. We can open a previous QTQt run with all the parameters we'll see we need to specify to run QTQt in an inverse mode. We can reload those parameters, and we can sort of restart an inversion run from where we stopped the previous one if we want to. We can look at output from previous runs, just if we haven't produced the graphics, we want to look at the results, or someone else can send us some output files, and we can look at those by opening previous summary files, output files. And finally, we can select if we want an output directory that's different to the default. And the default directory is just where the data files are, or where the last data file you open is. Okay, so what we'll do is say, let's try and build a new data file. So we go to build new data file, or on a Macintosh, Command N, probably Control N on Windows. Click that. And the first thing that comes up is this window. And so the way of building a data file, it's always in the same order for sort of historical reasons, that we start with Fission track age data, then Fission track length data, then helium data, and then vitrinite reflectance. And then finally, we put in some other parameters. We'll see that as we go through. If we have more exotic types of data like helium 4-3 spectra, argon 4039 spectra, detrital data, age profiles within single crystals, things are dealt with slightly differently, and that's explained in the documentation. So here I'm just going to talk about the really standard basic approach to putting in fission track data and helium diffusion data. Okay, so we see in this window, we have these little boxes that we can tab through. We need a sample name, so we can give the sample name whatever we like. We can put in X, Y, and Z coordinates in these three boxes, so longitude, latitude, elevation, effectively, but it can be any units you want. In general, the X and Y coordinates are not used. They will be in that's spatial modeling stuff, but at the moment, no. And the only coordinate that's really used for vertical profiles would be the elevation. So elevation is positive if we're going up a valley side towards the summit, and negative if we're in a borehole. Okay, and you just notice, I'll point this out here, at the bottom, this OK checkbox is not activated. And if you see that in QTQt, it's not activated because we need to put something in. Okay, so QTQt's waiting for some input values before it lets us progress. The only way we can progress, if we have no fission track count data, for example, we just click here, say no count data, and then I go to the next box, which is length data. But I can just return to the count data, fission track count data, by clicking there. And what we need to put in, clearly we need to put in some data, but one thing we have to put in is the name of a sample. Let's just call it test. And the default values for X, Y, and Z are all set to 0. We can change that as we like. And for the efficient track data, we put in by default number of spontaneous tracks, number of induced tracks, and some compositional parameter. And this is if we're using the EDM method. We have spontaneous tracks and induced tracks. And we might have composition that could be chlorine, it could be DPAR, it could be something else. But basically we have 3 columns we want to put in. If we don't have compositional data, we just leave that column blank. And we need to put in the minimum for EDM, external detector method data, the spontaneous tracks and the induced tracks. So I'm just going to go and find some data somewhere. I'll pause and I'll be back. Okay, so to build a data file, starting with some EDM data. So here on the right, I've got this Excel file, which is from the exercises prepared by Alicia and Mark. So it's some EDM data with NS counts, NI, spontaneous induced counts, and here a DPAR value, which just happens to be constant. So I can take these values and just copy them. And I would say here at this stage that there is sometimes some problems copying and pasting from Excel, most often with Windows, I think. I tend not to have problems, but I've heard sometimes people do. So if you have an Excel file and it doesn't work in terms of it might cause QTQt to crash, try just saving the columns like this to a text file and then using a text editor and pasting from there. So I'm just going to try and copy these columns. Yeah. I just go to the first line and I paste them in with Control V, Command V. And there we have the 20 columns, NS, NI, and in this case, the compositional value. That's fine, that's the first start. And then the other information we need for an external detector method age are these parameters here, zeta and the dosimeter density, rho d, and the number of tracks in the dosimeter. So I can probably quickest just to type those in. 0.61 e to the 5 and 2000. So once you've put in those values, you saw there quickly QTQt calculates the central age. It gives us the pooled age as well. It gives us an estimate of dispersion and tells us the chi-squared probability in the normal way. It also just gives us a summary at the top here of the number of crystals, what the average of the compositional parameter is. This is 2 because they're all, it's DPAR, we don't know that's DPAR yet. We need to find that later. It tells us what the average value is and the uncertainty or the standard deviation. So that's 2 plus or minus 0 because they're all 2. So the first thing you might want to do is if you're looking at data, but you probably should have done this before, is looking at the structure of the data, look at a radial plot, maybe looking at age composition. You can do that in QTQt, but there's other software that you might want to use to do that before. But if we look at the radial plot here, the default is this log transform radial plot. So here we have our radial plot with our data, and we see that the plus or minus 2 sigma normalized bands. We see there's a few data points fall outside that, which is probably why we get we fail the chi-squared test. Okay, I can change this to, if I turn off log transform and do a radial plot. Again, it's the normal non-log transform radial plot, but I think by default it's more common to use the log transform radial plot for efficient track data anyway. Another thing we can look at here is age versus composition. Not particularly useful in this case, as the compositions are all set to the same value. But if I do that, what I get here is the ages on the vertical axis and the compositional on the y-axis. If these data were dispersed, I'll create an example later on and show you how that looks. We can actually graphically subdivide the data into different groups if we want to, but let's not worry about that at the moment. So let's say this is all okay. We've put in these data, we're happy with that. And then I can go on now to say, okay, I'm going to go to the next stage and I'm going to put in some length data, vision track length data. And again, I'll come back to the data prepared by Alison Mark. So in here we've got length and angle to the c-axis. So I copy all of those and just paste them in. And by default, we don't have any compositional data on these length measurements, but by default, it will use the average, as is written up here, average composition from the count data of 2. We use the average of the count data. But if you have compositional data associated with your length measurements, it will use those input values that you define. The fact we've put in c-axis angle data lets us say we can use the projected tracks or not. So here we have the calculated mean track length and the standard deviation for the unprojected lengths. I can say I want to use projected lengths, and this will tell me what the mean and standard deviation of the projected lengths are. And then hidden a wee bit here just on the right, you get the projected lengths in microns to compare to the unprojected lengths if you ever want to do that. We can define Californium tracks if you want to, up to you. And just while we're on this window here, we can also use historical data if we have a histogram of lengths. Oops. We can read in histograms of lengths rather than the individual measurements associated with compositional data, or we can have just histogram values, which is with the number of tracks in each histogram bin. And we can deal with those kind of data here with open length data. And what QTQt will do is take the histogram data with the number of tracks in each bin. If you give the mean length and the standard deviation, so often in old papers you have those length distributions represented as histograms, and in a data table you get the mean length and the standard deviation reported. And QTQt can resample the histogram and produce a series of individual track lengths that give the same histogram and the same mean and the same standard deviation if you want that. Okay, so let's say okay there. If we're happy, I can, as I said, always go back to the count data, except that looks as though it's hung. Okay, so that happens with QTQt. It's probably a good place to stop. And I'll come back, I'll redo things and come back and we'll start again to go on to look at how we put in helium data. Okay, so I've restarted things. Here we are, I've put in the length data, and if I want to go back to counts again, I can do that in principle. Sometimes it crashes, as you saw. Not always. And if we're happy with the length data, as we've been put, I can say okay. And then we come to helium data, and you notice that the name of the sample and the XYZ coordinates are carried over each time, the same once we put them in. If I have no helium data, I can click on no helium data and go to the next window if I want to. But here we have some helium data in this data file. So we can either put in the age, and just point out that the age we put in is the uncorrected, un-FT corrected age. So it's the actual measured age, not corrected for alpha ejection, because the modeling in QTQt of helium diffusion deals with alpha ejection as part of the modeling process. So the predicted age is the uncorrected age. So you should put in the uncorrected age. If you only have the corrected age, if you have the FT correction factor, you can clearly just go back to the uncorrected age with the FT factor. Okay, so here we just have uranium, thorium, samarium concentrations in ppm and helium in nanocc's per gram. And you notice here there's different units you can use depending on how you get your data. I would say if you don't use QTQt to calculate an age, use some specific software, probably from the lab that does the analysis, because the age calculation, we need to know either the mass of the grain, we don't get to put the mass of the grain in here in QTQt, so it calculates the mass of the grain based on the grain dimensions you put in, and will calculate the age using that mass in certain cases, which is not always the most accurate way to deal with it. But let's say, okay, we've just got uranium 10 ppm, thorium 100 ppm, 0 samarium, you just leave that blank if you don't have any value, or treat it as blank, and then 100,000 nanocc's for helium. Okay, and just on this window, I can say calculate the age here. That does nothing until I put in the grain size. Okay. The other points here I won't talk about at the moment. You notice I can choose the mineral, so it's either apatite, and if you look down at the bottom here, these are the diffusion parameters, the activation energy, and D0, the diffusivity at infinite temperature, and the alpha ejection distance. There are some defaults in QTQt depending on the mineral you choose. So this is from Ken Farley's 2000 paper. If I choose to say this is actually zircon data, it changes to the Reiner et al. Paper from whenever that was, 2004, can't remember. Okay, and to calculate the age, generally, I need to put in the grain size. And you notice here we have 3 dimensions, length, width, and thickness. So it's treating the grain as a rectangle. And if I put in just one value here for length and leave these 2, width and thickness, empty, it will assume that value here is the equivalent radius, so R equivalent. So all the modeling is done by default as a sphere. Okay, there are different options we can choose, but the default is as a sphere. So just one value will be treated as the equivalent radius. If I put in, so we do have the width and thickness values here of 100 microns each of them. I can put in the width as 100. That will recalculate the equivalent radius. And if I do nothing more, if I leave the thickness blank, that will assume the thickness is the same as the width. So we'll assume it's 100. And even if I put in 100 here, the equivalent radius won't change because it's already assumed it's 100. Okay, and this calculates the mass for this rectangular parallelepiped grain using an assumed density for apatite, and that can be used to calculate the age. Here's written up here, 24.52 plus or minus 1.96. And here the 33.26 is the uncorrected age, the corrected FT corrected age, and the The 0.732 in red is the calculated FT factor that's used to correct the age. So in fact, you divide the 24.52 by 0.7372, you should get 33.26. Okay. And I'm just going to pause there. Okay. One thing you notice once I've put in the data, we've calculated the age. I'll just say this. If we only had the FT factor, sometimes you get data in papers where you don't get the grain size. You get the FT factor, so the equivalent of this 0.7372. You can actually put that value here in the length box with nothing else, and QTQt will calculate the equivalent radius with that value. So if this value is always less than 1, the FT factor, so we don't really expect a grain size of less than 1. So if we put in the FT value here, you see a little box will come up here where I've got R equivalent equals 60. On top of that, to say, do you want to convert this to equivalent radius? You check that box. You'll end up with the equivalent radius of 60 or very, very close to 60. Okay. So the other thing that you might notice here is the helium ejection distance, alpha ejection distance, has changed a little bit. It was 20 by default. In fact, we calculate that value based on the concentrations of uranium and thorium and their respective, and samarium if we have it, their respective ejection distances for different isotopes. Okay, then the final thing we can do here is we can choose a radiation damage model. So we have the model of Gautron 2009, Flowers 2009 for apatite, Guntner 2000, and I can't remember quite when it was, sorry, for zircon. Another model that came out of the Gautron group in Paris, which is a slight modification of the original model for apatite. A model published by Chelsea Willett for apatite radiation damage model, and more recently the Ginster model, who's developed again by Willy Guntner based on the paper by Ginster et al. For zircon. So there's 2 zircon models and 4 apatite models, and as you see, I've got a default here of apatite. If I choose, for example, the Guntner model, which is for zircon, we'll see QTQt tries to anticipate. We'll change this to zircon, and we'll fix the activation energy, the kinetic parameters for diffusion to the default for that published model. So you can't change them once we choose a model. If I choose the Gautron model, that will jump back to apatite, and again use the default diffusion parameters from the published paper. Okay, there's some other things in this box that we won't really worry about. If I have more than 1 grain, I can just click here, add another age, and I keep going. It will be the same dialog box that comes up. You put in the same information and keep going like that. If you have 10 grains, you do that by hand. We'll just leave this with 1 grain. And the model preferred here was the Flowers model, actually, in the Excel table. Okay, so we see again the kinetic parameters change, and we say okay. And then the next box that comes up is for vitronite reflectance data. If you don't care about that, we just say we have no vitronite data. Then the final box that comes up is allows us to put some sample specific parameters. In particular, here we have a little summary. There's fission track data of the central age and the mean track length. This first part here allows us to put in a constraint related to time and temperature, which the relevance of this is most likely for sediments where you have a stratigraphic age. So you'd put in, the stratigraphic age plus or minus something, so 100 million years plus or minus 10 would give us a range of 90 to 110 million years. and you put in a temperature, say 15 degrees plus or minus 5, to capture the range from 10 to 20 degrees centigrade. We can do the same for the present day temperature, and this is again most useful perhaps for sediments in boreholes. We can put in the present day temperature, the mean value plus a range. So it's, you know, the 60 degrees plus or minus 5 would give us a range of 55 to 65 degrees. I won't do it for this sample. You can look in the documentation. And the final thing related to that is we can, for sediments, we can say we allow for pre-depositional thermal history. That is, QTQt can add in a time temperature point prior to deposition. So the deposition will be defined by this time temperature constraint, usually the stratigraphic age when the sample is at the surface. And QTQt can add a point for each sample that's independent of all the other samples to allow for some kind of pre-depositional thermal history that could be preserved in the sample, some provenance related thermal history if the sample hasn't been totally reset, either in terms of fission track annealing or helium or both. It doesn't really matter. Okay. And then here we can choose the annealing model we want. So these are the classic models from Richard Ketchum. It's two models for annealing and apatite, the original Laszlo model. And then the last three are models from Takatagami's group for zircon annealing. So depending whether you've got zircon, it's here you decide whether you're dealing with apatite or zircon in the original fission track data. And we need to choose, so we put in some kinetic proxy parameter here. Look on the right, the data table here. It's a dpar value, so I just select, this is dpar, my compositional model. It tells me the value I've put in of 2. There's no dispersion or uncertainty on that value. All the values are set to 2. And having chosen the Ketchum et al. 2007 model, there's some things that are default. We would calculate the initial track length and so on from the compositional data. And so we can choose a range of different compositional proxies that can be injected into the annealing model as we like, and we can choose different etchants as we like. Okay, and then the last thing here is the helium data. This just summarizes that we've got one helium age. We've chosen the Flowers model for radiation damage. We've got Novich data. I can always change that if I want here. And I guess I should say here that the mixed model is if we could have a mixture of zircon and helium and apatite helium data in the same data file. So we might use different radiation damage models for those. And we put in the radiation damage model for each grain we're dealing with as we enter the data. Okay, and then I can save the data for reload. Again, you'll notice here this OK checkbox is not activated, and that can be just because we need to tab out of some boxes. We'll put in a value here. If you ever get that, try that. Okay, that hasn't worked. Usually means we're waiting for something, and it's not clear to me exactly what we're waiting for there. But I can always just click this box is always activated, save data for reload. This will just save the data file. If I click that box, it takes the name of the sample. So at the top here, the sample, I just called it TIST. We'll use that by default, and it was what the default directory is where I'm actually running QTQt. So I can go here to this directory where I'm building the data file, and I just call it test1, and I just save the data file there like that, and then I can okay, so there I've built a data file, and what we look at here in the file menu, you see that file I've just created is put to the top of the list of recently opened files, so I can just open that file directly if I want to do something with it, if I want to run something, whatever. Okay, and then just the final point here is on the right here is the data file that's created from by Lucia and Mark. So my output file should look like this, more or less. If something's changed slightly here in the, perhaps I've done that manually to change the compositional parameter, but here we see the structure of the data file. There's a few lines here. This is all described in the appendix of the documentation. If I can find that. Not that one. Sorry. It'd be useful just to show you that. So here is the famous documentation, and so somewhere near the bottom is an appendix that has effectively the structure of the data file here, appendix 1. It tells you what each line is. And there's lots of little footnotes here that try to explain things. And in other places in the documentation, you'll find little descriptions of how that data file structure can vary. But effectively, the data file is just a text file, and it always has a pretty similar structure. So we've got the count data here, these columns here, NSNI, and we've got the length data with the angle to the z-axis. Some of these parameters up here tell us how many. We've got 100 lengths, 20 counts, blah, blah, blah. At the bottom, we've got the helium data with how many grains we've got. This is a flag for the radiation damage models. These are the concentrations of uranium, thorium, helium. This is the age, this is the grain size parameters. And these are some of the diffusion parameters. Again, the radiation damage model for that particular grain, and the geometry, whether we're dealing with a sphere or a slab or a cylinder. But that's all explained in the documentation. But you can see, in principle, it's just a text file. And once you get used to what the structure of these, often it's easier just to build the data file by hand. You avoid those problems with QTQt crashing for unusual reasons. Okay, so there we've built a data file, the data file from example 1, and we'll stop there and we'll come back and we'll perhaps look at running a data file, but I'll do that with different data files, and we'll see how we input some of the parameters to do model runs. Okay.